Welcome to ninth lectures on terpenes and terpenoids. In this lecture, we are going to discuss about the chemistry of Santonin molecule. In previous lectures, we have discussed the chemistry of farnesol as well as gingiberine. Farnesol and gingiberine belongs to a class of sesquiterpenoid. Similarly, Santonin is a third example belonging to a class of sesquiterpenoid. We'll discuss the chemistry of Santonin in very detail. First of all, we will see the occurrence as well as uses of Santonin. We will discuss the structure of Santonin on the basis of chemical methods of analysis. Santonin and santonamide undergo very interesting rearrangement reactions. It shows Wagner-Irwin rearrangement as well as a diene-phenol rearrangement. So we will discuss these two reactions in detail. Now, first of all, let us see from where we get this Santonin molecule. Santonin, the major source of the Santonin is Artemisia sina. This Artemisia sina is having lot of medicinal property. It is used as anthelmintic. Anthelmintic means it is useful in the killing of roundworms, and doses of 60 to 200 milligrams daily for 3 days is sufficient. But due to toxicity effect, nowadays it is replaced by other anthelmintics. Now let us discuss the structure of Santonin on the basis of chemical methods of analysis. Earlier, the chemists were not having sophisticated tools, and therefore they were reaching to the structure of Santonin on the basis of chemical methods of analysis. In chemical methods of analysis, first of all, scientists carry out the estimations of carbon as well as hydrogen, and from the estimations of carbon and hydrogen they reached to the molecular formula of the Santonin, and it was found to be C15H18O3. Now from this molecular formula we get a lot of information about the structure of Santonin molecule. Now this 15 number of carbon atom indicates that there are 3 isoprene units present in Santonin, and according to the isoprene rule we may assume that these 3 isoprene units may be joined through head to tail linkage. Now since it contains 3 isoprene units, it belongs to a class of sesquiterpenoid. So apart from this broad idea about the structure of Santonin, another information we get about this molecule is the degree of unsaturations or the double bond equivalence. Degree of unsaturations or the double bond equivalence is nothing but the how many double bonds or the ring is present in this molecule, and it is calculated for a molecule CXHYOZ by the formula x plus 1 minus y by 2. So if you keep the values of hydrogen as well as carbon in this formula, the degree of unsaturation in Santonin is found to be 7. So 7 degree of unsaturation in Santonin, it means that Santonin may contain 7 double bonds, it may contain 7 rings, or it may be the combinations of some double bond plus ring. So in the incoming investigations, we have to find out the nature of this unsaturation. So to find out the nature of this unsaturation, the simple experiment of hydrogenation is carried out. When Santonin is subjected to hydrogenation in presence of catalyst, it forms tetrahydrosantonin. So if you subtract the molecular formula of the Santonin from the hydrogenation product of Santonin, then it is observed that Santonin has consumed 2 molecules of hydrogen. Now consumptions of 2 molecules of hydrogen by Santonin clearly indicates that there are 2 double bonds in Santonin. So out of 7 unsaturations, we have accounted for 2 degree of unsaturations due to the presence of 2 double bonds. Now let us find out the nature of oxygen. Here there are 3 oxygens in the formula of the Santonin, and for that we have to do some experiments. One of the experiment is the treatment with alkali. When Santonin is treated with alkali, it is found that it forms a sodium salt of this hydroxy acid. Now the formations of hydroxy acid is only possible only when we assume the starting material as a lactone type of the moiety. So since Santonin forms here hydroxy acid, it means that Santonin molecule is a lactone. In other words, out of 3 oxygens, we have accounted for the nature of 2 oxygen in the form of lactone. Now this presence of lactone is again supported from the IR data. IR of Santonin shows a strong peak at 1770 centimeters inverse, and this is a characteristic signal of gamma lactone. So on the basis of this simple experiment, that's the reactions of Santonin with NaOH forming hydroxy acids gives us 2 information that there is a presence of lactone ring. Lactone ring may lactone ring contains 2 oxygens, so out of 3 oxygens we have got the nature of two oxygens, and secondly lactone corresponds to the presence of one ring here. So one ring and the one carbonyl here, there are total 2 degree of unsaturations corresponding to lactone. So out of 7 degree of unsaturation, the presence of lactone accounts for 2 degree of unsaturation. So in this way we have progress here. Total 7 degree of unsaturations. Presence of two double bonds are proved from hydrogenation experiment, and the presence of lactone corresponding to 2 degree of unsaturation is proved from the reactions of Santonin with NaOH. Now let us find the nature of third oxygen. Santonin, when it is treated with hydroxylamine hydrochloride, it forms oxime derivative, and formations of oxime derivative is a characteristic reaction of carbonyl compounds. And it is also found that this carbonyl group is to be a ketonic. So on the basis of this experiment, chemists reached to the conclusion that the third oxygen present in Santonin molecule is ketonic in nature. So in this way, we have proved the nature of three oxygen. Two oxygens are part of the lactone moiety and one oxygen is form of the ketone moiety. Now ketone corresponds to again 1 degree of unsaturations. So in this way, we have accounted now total 5 degree of unsaturations. 2 is for double bond, 2 is for lactone, and 1 is for here ketonic oxygen. Now the nature of this ketone is found to be an alpha beta unsaturated, and it is based upon the UV spectrum data. Santonin shows lambda max at 236 nanometer, and it is a characteristic lambda max for the alpha beta unsaturated ketone pattern, and therefore we believe that the Santonin molecule is an alpha beta unsaturated ketone. So in this way, we have now we have reached to these structural features of the Santonin molecule. Presence of two double bonds and three oxygens are in the form of lactone as well as a ketone. Now it's time to accommodate this one, two double bonds, lactone, moiety, and ketone, and for that we must get an information about the skeletal of the Santonin. And for this we are having a very interesting experiment. Santonin, when it is subjected to the zinc distillation, it forms the naphthalene derivative plus some quantity of the propylene is also formed. Now the formations of naphthalene clearly indicates that this Santonin molecule contains these two rings. It's a dihydronaphthalene skeleton is likely to present in structure of Santonin molecule. So presence of naphthalene corresponds to 2 degree of presence of naphthalene skeleton corresponds to the 2 degree of unsaturation. So in this way we have accounted for 7 degree of unsaturation. Two double bonds are proved on the basis of hydrogenation experiment. Presence of lactone is proved on the basis of uh, hydrolysis experiment. Presence of ketone is proved on the basis of oxime formations, and the distillations of Santonin with zinc proves the presence of naphthalene skeleton. So in this way we have accounted for 7 degree of unsaturation. Now in this naphthalene skeleton we have to accommodate this two double bond as well as the where the lactone ring is fused with the naphthalene ring and the positions of ketone. So if we do these things, we will reach to the structures of the Santonin molecule. And to accommodate to find out the positions of double bond as well as ketone, here some interesting experiments are performed. In one of the experiments, Santonin is reduced with Santonin is reduced in presence of certain catalyst, and we get a tetrahydrosantonin. Here the ketone group is intact, and this ketone can undergo a Clemenson's reductions, and we will get a deoxy tetrahydrosantonin. So this deoxy tetrahydrosantonin, here the two oxygen are remaining intact and perhaps it's a part of our lactone moiety. So this deoxy tetrahydrosantonin on selenium dehydrogenations gives us 7-ethyl 1-methyl naphthalene molecule. The same molecule is obtained again from hydrogenation. Here complete hydrogenation is performed. Carbonyl group is converted into hydroxyl and the two double bonds are converted to saturated hydrocarbon. So we get here hexahydrosantonin, and the distillations of hexahydrosantonin with selenium again results in the formations of 7-ethyl 1-methyl naphthalene. Now the formations of 7-ethyl 1-methyl naphthalene is possible only when we assume this skeleton present in Santonin molecule, because in both the cases we are getting methyl here and here we are also getting the linkage of this ethyl group on this side. So this experiment has proved that Santonin molecule is having this structure accounting for 13 number of carbon atoms, and the 2 number of carbon atoms are still not accounted here. Now, during selenium dehydrogenation, it is well-known fact that the angular methyl groups as well as the carboxyl groups are lost. So, one carbon atom which is likely to be a part of lactone moiety will be converted into carboxylic acid, and that carboxylic acid will be lost in the reactions. So, in this way, we reach to the 14 number of carbon atoms, but the positions of one carbon atom is still left, and it is chances that this methyl group must be perhaps present at the angular position, but we should have some chemical evidence regarding this kind of the hypothesis. Now let us see here how much we have progressed. We have proved here 7 degree of unsaturation, 2 double bonds, lactone, ketone, and naphthalene skeleton. We have already made a discussion, and now the previous experiment, that's a selenium dehydrogenation of Santonin molecule leads to form here this naphthalene, where the methyl as well as ethyl groups are present on these positions. Now in this molecule we have to again put here, this is a total 13 number of carbon atoms. We have to put the positions of 2 double bonds as well as the keto group, and for that this experiment is performed. Santonin on reactions with the hydroxylamine hydrochloride, it forms oxime, and oxime is reduced in presence of zinc S2SO4, it forms a santonamine. So we got here primary amine. Oximes on reductions gives a primary amine, and the primary amine undergo diazotization reactions using the nitrous acid, and it leads to form a molecule called as hyposantonin. So in this case, no carbon atom is lost, only some sort of rearrangement has occurred, and if we can reach to the structure of hyposantonin, then one can understand the structure of santonin very easily. So this is an experiment, and in this experiment the structure of hyposantonin was elucidated on the basis of various reactions. When hyposantonin is oxidized with KMnO4, it forms 3,6-dimethyl phthalic acid, and the formations of 3,6-dimethyl phthalic acid clearly indicates that it is this ring which is likely to contain the 2 double bonds attached to a saturated ring, and because of that dicarboxylic acid is formed on this side of the molecule. Another is reactions with the molecular iodine forms a santalinic acid with these 2 methyl groups attached at 1,4 positions, and this also undergo decarboxylations and we get this molecule. Same molecule is obtained by its hydrolysis of hyposantonin with HCl undergoing dehydration, and its reactions is distillation with the barium hydroxide gives us this molecule. Now the formation of this molecule, particularly this molecule, is possible. Here we have already said is a skeleton. Methyl and the ethyl groups are here, but this methyl group is now appearing on this side every time. And the attachment of this methyl group here is possible only when we assume the structures of hyposantonin here in this way. This is subjected to oxidations. Here this ring is cleaved. Then on reactions with the molecular iodine, again it undergo dehydrogenation, and with HCl it undergo ring opening followed by dehydration and distillation. So in this way we reach to the structures of the hyposantonin. Now hyposantonin is formed from santonin, and therefore one can reach to the structures of santonin molecule in this way. So if we assume the structures of hyposantonin, then it is we can write the structures of santonin in this way, where the methyl group and the isopropyl groups are here. We have already kept the evidence, and the positions of these 2 double bonds we are keeping on this side of this naphthalene skeleton, because this is a becoming aromatic in nature, and we are keeping here angular methyl groups deliberately because during selenium dehydrogenation it was lost. So if you assign the structures of santonin as it is written here, then one can understand all our previous evidences very well. So let us see how, if we assign this structure, we have to convince ourselves how these remaining products are formed. For example, here the hydrogenation experiment of double bonds gives a ketone, and ketone is subjected to Clemens reductions. We get a deoxy tetrahydrosantonin, and this on selenium dehydrogenations removes these angular methyl groups, and that's why we got 1 methyl 7 methyl naphthalene. So the structure of santonin is inconsistent with what was the chemical evidence we got in the previous discussion. Similarly, here complete hydrogenation of two double bonds as well as ketone gives us hydroxy Santonin, and then its distillations with selenium again forms 1 methyl 7 ethyl naphthalene. So on the basis of this data we reach to the structure of Santonin molecule. Similarly, Santonin forms oxime and its reactions with the reduction with zinc S2SO4 forms santonamide, and the reactions of santonamide undergo diazotization or some rearrangement reactions to form the hyposantonin. So we have now convinced ourselves. Similarly, it forms a hydroxy acid, and the structure of hydroxy acid will be like this. So if you assign the structures of Santonin molecule in this way, we can understand the outcome of all the previous experiments which were carried out to illustrate the structure of Santonin molecule. So we have completed the structure determinants of Santonin on the basis of very simple experiments. Now here we have to convince ourselves how this rearrangement has occurred. Santonamide reacts with the nitrous acid and here hyposantonin is formed. There was a main issue related to the positions of this methyl group in santonamide, and therefore this Wagner-Merwin type of the rearrangement that's involving diazotization as reactions, we have to convince ourselves, we have to understand the mechanism of this reaction. So reactions of one nitrous acid with the another nitrous acid form the nitrosonium ion. Nitrosonium ion is an electrophile and it participates in a diazotization reactions, and we get a diazonium salt at the end. Now this N2 is a very good living group, and when it is lost we get here a carbocation, and this carbocation undergo allylic rearrangement, it undergo Wagner-Merwin rearrangement. Here 1,2 methyl shift is occurring and we get another carbocation, and finally this carbocation uh, is converted into an aromatic substrate. So the driving force for the Wagner-Merwin rearrangement is the formations of aromatic compound at the end. So in this way the hyposantonin is formed, and hyposantonin formation is possible only when we assume this methyl group at the angular position. Another interesting rearrangement that Santonin show is a dinone-phenol rearrangement. Here dinone is converted to phenolic compound. Again this methyl group is from angular position is migrating to the these positions leading to form 1,4-dimethyl type of the compound. So it is protonated here. Santonin molecule is protonated here, and after protonations we get a allylic shift. After allylic shift we get here a secondary carbocation. Secondary carbocation will try to achieve more stability to get converted into tertiary carbocation. So it participates in a Wagner-Merwin rearrangement and we get a tertiary carbocation. This tertiary carbocation is converted into Santonin in a reactions called as diene phenol rearrangement. So these two rearrangements are very important from mechanism point of view. Now once this Santonin chemistry is learned, now it's time to check our progress, how much we have learned, and for that we should undertake some problems. This is usually a practice in organic chemistry, and here few problems I have included in the discussion. Here, this problem is related to the some experiments carried out in the structural isolation of Santonin. So here there are certain evidences, and from these evidences we have to reach to the structure of the structural features of the Santonin molecule. For example, its molecular formula is C15H18O3. Now, how many informations we get from this molecular formula? IR shows 1770 centimeter. It means it's the presence of lactone. It forms a hydroxy acid. It means again in lactone. On distillations, it forms naphthalene derivative. So Santonin contains a naphthalene skeleton, and it forms oxime derivative. So on the basis of this chemical evidences, students should write the chemical, or students should write the structural features of the Santonin molecule. Another problem is related to the mechanism of the reactions. Santonin molecule undergo diazotization to form the hyposantonin. Similarly, santonin undergo rearrangement reactions to form the demotroposantonin. In both the cases, we get a 1,2 methyl shift involving the Wagner-Merwin type of the rearrangement, and therefore the students should understand this mechanism very well. So in this way, we have completed the santonin molecule. Now in the next lecture, we will deal with the class of diterpenoid, phytol, abitic acid and the vitamin A. These three molecules belong to a class of diterpenoid. We will discuss their chemistry in detail. Thank you. Thank you very much for watching this video. Subscribe the video, like the video and stay tuned with chemistry. Thank you very much.